Today's question is, what creates space and time? Now, I want you to stop whatever you're doing and just hold your hands out in front of you. Move them about a foot apart. Look at the gap between them. What is in there? You might say, well, Richard, there's air in there. Okay, so we pump the air out. We put you in a vacuum chamber. Now, what's between your hands? Nothing, you say. Empty space. But what is that empty space? Is it just a big, dark, empty box where the universe happens? A stage where the actors, the stars, the planets, you and me, walk around and do our little dance? And what about the time it took for you to lift your hand? Is time just a universal clock ticking away in the background? Tick-tock, tick-tock, the same for everyone, everywhere, forever? For thousands of years, the smartest people on Earth thought exactly that. But nature, you see, is much more imaginative than we are. When we actually started looking closely at how the universe behaves, we found out something absolutely shocking. That empty space, it isn't empty, it isn't a box, it is a physical thing. It bends, it stretches, it ripples, it can be warped, and it can be torn. And time isn't a background clock. Time is subjective, malleable, and inextricably woven into the very fabric of space itself. But that brings us to the ultimate cliffhanger, the mystery that keeps modern physicists awake at night, staring at the ceiling. If space and time are a fabric, a physical substance, where did the fabric come from? What is it made of? If you take a magnifying glass and zoom in on empty space, past the atoms, past the quarks, past the tiniest things we can measure, what do you see? Do you see smooth emptiness, or do you see pixels? Do you see the gears and springs of reality? Does space have atoms of its own? And if we can find the atoms of space, does that mean space and time are not fundamental, but are actually created by something deeper, something entirely alien to our everyday experience? So stick with me, because over the course of this journey, we are going to dismantle the universe piece by piece. We are going to throw away your common sense, because common sense is just the prejudices you acquired before the age of 18. We are going down into the microscopic basement of reality. By the time we are done, you're going to look at the empty space between your hands, and you're going to see a boiling, frothing ocean of quantum entanglement, a holographic projection from a boundary at the edge of infinity, a mirage born out of the rules of probability. Let's start with the illusion we all live in, the Newtonian illusion. Isaac Newton, a very smart guy, built his whole theory of physics on a simple idea. Space is absolute, and time is absolute. To Newton, space was a rigid coordinate system made of nothing, stretching out to infinity. Time was God's watch, ticking uniformly everywhere. If I snap my fingers, that moment in time is happening for me, for a guy on Mars, and for an alien in the Andromeda galaxy simultaneously. It makes sense, right? It feels right. But then at the beginning of the 20th century, a patent clerk named Albert Einstein comes along and says, wait a minute, let's actually look at how light behaves. People had measured the speed of light, and they found something bizarre. No matter how fast you're moving toward a light beam, or how fast you're running away from it, the light always approaches you at the exact same speed, 186,000 miles per second, always. Now, if you think about it for just a second, that is completely crazy. If I throw a baseball at 100 miles an hour, and you drive toward me in a car at 50 miles an hour, that ball hits you at 150 miles an hour. That's just basic addition. But if I shine a flashlight at you, the light comes at you at the speed of light. If you jump into a rocket ship and fly toward me at 99% the speed of light, you would expect the light to hit you at almost twice its normal speed. But it doesn't. You measure it, and it's exactly the speed of light. It doesn't care how fast you're moving. Einstein realized that if the speed of light is absolute, then the things we use to measure speed, distance and time, must be flexible. Speed is just distance divided by time, space divided by time. If the answer to that equation, the speed of light, never changes, then the top and bottom of that fraction have to change. And this means that if you move really fast, your clock has to tick slower compared to mine to keep the speed of light constant. Your ruler has to physically shrink. Space and time are not rigid. They are rubbery. They are trading places with each other. Einstein said, look, space and time are not two different things. They are the same thing, just looked at from different angles. They form a four-dimensional fabric called space-time. A decade later, Einstein went even further. He asked, what is gravity? Newton thought gravity was a mysterious invisible rope pulling massive objects together instantly. Einstein said, no, there are no invisible ropes. Gravity is just the shape of this space-time fabric. Imagine a trampoline. You put a heavy bowling ball in the middle, the canvas sags. Now you roll a little marble across the trampoline. It doesn't go in a straight line. It curves around the bowling ball, maybe spiraling down into it. The bowling ball didn't reach out and grab the marble. The bowling ball warped the fabric of the trampoline, and the marble is just following the new curves of the fabric. That is what a star does to space and time. The Earth is going around the sun, not because the sun is pulling it, but because the sun has bent the space around it into a giant ball, and the Earth is just rolling along the rim of the ball. But here's where the story gets really interesting. Einstein's general relativity tells us how space-time behaves. It tells us it can bend. It tells us that if you get enough mass in one place, you can create a black hole. Space-time can bend so infinitely deep that it forms a hole, a black hole, where time literally stops. It even tells us that space-time can expand, stretching out like a rubber band, which is what our universe is doing right now. But general relativity does not tell us what space-time is made of. Einstein's equations treat space-time as a completely smooth, continuous sheet, like a perfect puddle of water. You can zoom in 1,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times, and it will always look perfectly smooth. You can cut a millimeter of space in half and half again and half again forever. But is that true? Does nature really allow you to cut something in half forever? Let's leave the world of stars and galaxies and enter the microscopic world, the world of quantum mechanics. The rules down here are completely different. Down in the subatomic world, nature is not smooth. Nature is chunky, it's pixelated. If you look at light, it seems like a continuous wave. But if you zoom in, you find it is made of tiny indivisible packets, little bullets of light called photons. If you look at an electric current, it's not a smooth river, it's a parade of individual electrons. Energy, matter, charge, spin, everything in the quantum world comes in discrete, indivisible units called quanta. You can't have half a photon. You can't have half an electron. So in the 1930s, physicists started asking a very profound, terrifying question. What about space? What about time? Are they continuous, like Einstein thought, or are they quantized, like everything else? Is there a smallest possible piece of space, the smallest possible tick of time? Let's do a thought experiment. It's the best way to do physics without a laboratory. Let's try to measure a smaller and smaller piece of space. To see something very small, you need a microscope. But not just any microscope. You see, to resolve a tiny object, you have to hit it with light that has a wavelength smaller than the object itself. If the waves are bigger than the object, they just wash over it like ocean waves over a tiny pebble, and you don't see a thing. So to see a tiny piece of space, you need light with a very, very tiny wavelength. But here's the catch. In quantum mechanics, the shorter the wavelength of a photon, the higher its energy. Think of a long, lazy ocean wave. It doesn't have much punch. Now think of short, choppy, rapid-fire waves, and they carry a lot of energy. So to measure a billionth of a millimeter, you need a high-energy photon. To measure a trillionth of a millimeter, you need an even higher energy photon. Now let's push it to the absolute extreme. Let's try to measure a piece of space so unimaginably small that it is 10 to the power of minus 35 meters across. That's a decimal point, 34 zeros and a 1. To resolve a piece of space that small, you need a photon with a wavelength that small. But to get a wavelength that small, you need an absolutely enormous amount of energy packed into that tiny photon. Now remember Einstein, E equals mc squared. Energy and mass are the same thing. If you pack a huge amount of energy into a ridiculously tiny volume of space, what happens? The energy becomes so dense that its gravity collapses the surrounding space-time. You create a microscopic black hole. The moment you try to look at a piece of space this small, you will be sucked into it. Your light collapses the very space it was trying to illuminate. Nature throws up a brick wall. It puts up a do not enter sign. It physically prevents you from measuring anything smaller than this distance. This ultimate limit is called the Planck length, and the time it takes light to cross that distance is the Planck time, 10 to the power of minus 43 seconds. These are the pixels of reality. If you cannot measure anything smaller than the Planck length, not just because of bad technology, but because the fundamental laws of physics forbid it, then it means space doesn't exist below that scale. It means space is not continuous. Space is made of little chunks, pixels, atoms of space. But what does it mean to have an atom of space? An atom of gold sits inside space. An atom of oxygen floats through space, but an atom of space, it doesn't sit in space. It is space. This realization destroys Einstein's beautiful, smooth trampoline. If you take a magnifying glass to the trampoline, it isn't smooth at all. It is woven out of individual threads. John Archibald Wheeler, a brilliant physicist, realized that at the Planck scale, quantum uncertainty goes completely crazy. You know Heisenberg's uncertainty principle. You can't know exactly where a particle is and how fast it's moving at the same time. The more you know one, the less you know the other. Well, this applies to fields too. It applies to space-time. At the macroscopic level, space-time looks calm and flat. But as you zoom into the Planck length, the geometry of space itself begins to wildly fluctuate. It writhes, it boils, it tears and repairs itself in fractions of a second. Wheeler called this the quantum foam. Imagine you're flying high above an ocean in an airplane. You look down and the ocean looks completely smooth, like a blue pane of glass. But then you parachute out. You get closer and closer. The smooth surface starts to look textured. You see ripples. Then you hit the water and you realize it is not smooth at all. It is violently crashing, splashing, frothing with bubbles popping and churning everywhere. That is the fabric of our universe. So if space-time is a boiling foam of microscopic pixels, how do these pixels hook together to create the big smooth universe we live in? How do we build space from scratch? One of the most profound attempts to answer this is a theory called loop quantum gravity. Now, I want you to pay close attention because this idea completely shifts how you have to think about reality. In loop quantum gravity, they say, let's stop pretending space is a stage. Let's build the stage out of relationships. Imagine you have a bucket of chainmail rings. If you just dump them on the floor, they will be crushed. They are just a pile of rings. But if you take pliers and link them together, 4 rings to a center ring in a repeating pattern, you suddenly have a sheet of armor, a fabric. Loop quantum gravity suggests that space is constructed by tiny, discrete loops of gravitational field. They are mathematically described as spin networks. A spin network is like a microscopic game of connect the dots. Each dot, or node, represents a tiny volume of space, not a volume in space, but the volume of space, the ultimate atom of volume, exactly 1 Planck volume. The lines connecting these dots represent the area between these volumes, how they interact. When you have billions and billions and trillions of these nodes linked together, they weave a 3-dimensional web. From a distance, this web looks completely continuous, just like how the fabric of a cotton shirt looks continuous until you look at it under a microscope and see the individual woven threads. In this view, movement isn't a continuous line. When an electron moves from point A to point B, it isn't gliding through empty air. It is jumping from one node of the spin network to the next. The universe is a computer, updating its state tick by tick, Planck time by Planck time. But wait, we have another contender in the ring, a heavier weight, string theory. String theory approaches the problem differently. It says that the fundamental ingredients of the universe are not little dots, but microscopic vibrating strings of energy. But to make the mathematics of string theory work without producing nonsensical answers, like negative probabilities, the math demands something outrageous. Our universe cannot have just 3 dimensions of space and 1 of time. It must have 10 or even 11 dimensions. Now look around you. Up, down, left, right, forward, backward. That's 3. Where are the other 7? String theorists say they are curled up, compactified into little microscopic geometric knots, Calabi-Yau manifolds hiding at every single point in space. But how does string theory explain the creation of space? Through one of the most magnificent and mind-bending discoveries in the history of human thought, the holographic principle. To understand the holographic principle, we have to talk about black holes. You see, black holes are the ultimate test laboratories for physics. They are places where gravity is enormous, general relativity, but crushed into a tiny point, quantum mechanics. If you want to know how space and time work, you have to figure out what happens inside a black hole. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered something crazy about black holes. A black hole has a boundary called the event horizon. It's the point of no return. If you cross it, you are gone forever. Bekenstein and Hawking figured out that when things fall into a black hole, the information about those things, the quantum data of what they were made of, doesn't just vanish. It gets smeared out and stored on the surface of the event horizon. And here was the kicker. The amount of information was so overwhelming that it was impossible to process it all at once. A black hole can hold is strictly proportional not to its volume, but to its surface area. Let that sink in for a moment. Think about a library. If you want to store more books in a library, you need a larger room, you need more volume. But a black hole doesn't work like that. It stores information like a hard drive, but the capacity of that hard drive is determined by the square footage of the surface of the black hole, not the cubic footage of its inside. It is exactly as if the three-dimensional interior of the black hole is entirely described by a two-dimensional layer on its surface. Physicists stared at this and thought, hold on. A black hole is just a region of space. If the 3D interior of a black hole can be completely encoded by its 2D boundary, could the same be true for the whole universe? Imagine a hologram on a credit card. It's a flat two-dimensional piece of plastic, but if you shine light on it, a three-dimensional image pops out. All the information to make the 3D image is mathematically encoded on the 2D surface. In 1997, a brilliant physicist named Juan Maldacena published a paper that turned physics upside down. It's called the ADS/CFT correspondence. It's a mouthful, but the idea is pure magic. Maldacena mathematically proved that a three-dimensional universe with a four-dimensional space-time gravity, like ours, governed by string theory, is mathematically identical to a two-dimensional boundary without gravity, governed by quantum field theory, wrapping around it. They are two completely different languages describing the exact same reality. A 3D world with gravity on the inside and a 2D world without gravity on the surface, and the mathematics match perfectly. What does this mean for the creation of space? It means that space, the 3D room you are sitting in right now, might be a magnificent illusion. It might be a holographic projection. The real physics, the fundamental machinery of the universe, might be happening on a flat boundary infinitely far away. The distance between you and the wall, the depth of the cosmos, the volume of the sun, none of it is fundamental. It emerges from the flat surface of reality like a 3D video game rendering out of the 1D code on a computer hard drive. You are a hologram thinking you have volume, living inside a hologram wondering where the volume came from. But how? How does the 2D boundary project the 3D space? What is the projector? What is the light? The answer brings us to the most cutting-edge, astonishing idea in physics today. It is the idea that space is created by quantum entanglement. As you see, in the 1930s, Einstein, Podolsky, and Rosen, EPR, pointed out a flaw in quantum mechanics. They realized that if the math of quantum mechanics was true, two particles could become entangled. That means their properties become perfectly linked forever, no matter how far apart you pull them. And if I have an entangled pair of electrons, I can keep one here on Earth and send the other to the far side of the Milky Way. If I measure my electron and find it spinning up, I instantaneously know with 100% certainty that the electron across the galaxy is spinning down. Einstein hated this. He called it spooky action at a distance. He said, nothing can travel faster than light. So how can my measurement here instantly dictate the state of a particle 100,000 light years away? He thought it proved quantum mechanics was incomplete, but over the last 50 years, experimentalists have proven Einstein wrong. Entanglement is real. It happens. It is the core feature of the quantum world. But the mystery remains. How do they communicate? How are they connected across the vast empty ocean of space? Let's go back to Einstein's other great theory, general relativity. In 1935, the exact same year Einstein wrote his paper on quantum entanglement, EPR, he wrote another paper with Nathan Rosen. This one was about black holes. They found that the math of general relativity allowed for a tube, a tunnel through space-time connecting two different black holes, a shortcut and a wormhole. In physics, we call an Einstein-Rosen bridge an ER. So in 1935, Einstein discovered two weird things: entanglement, EPR, and wormholes, ER. For 80 years, physicists thought these were two completely different phenomena. One was a weird quantum trick with subatomic particles. The other was a massive gravitational tunnel made of space-time. But recently, physicists like Leonard Susskind and Juan Maldacena put two and two together and arrived at a beautifully elegant equation, ER equals EPR. Entanglement is wormholes. They suggest that when two tiny particles are entangled. They are not communicating magically faster than light across empty space. Instead, they are physically connected by a microscopic wormhole, a tiny subatomic tunnel through the fabric of space-time. The entanglement creates a geometric link. Now let's scale this up. What if we take this idea to its logical absolute conclusion? If entanglement creates tiny threads of space between particles, what happens if we entangle billions, trillions, octillions of particles? You get a massive interwoven web of microscopic wormholes. You get a fabric. Susskind and others propose that empty space itself is nothing more than a vacuum, the geometric manifestation of quantum entanglement. Space is the glue of entanglement. The reason you can move your hands through the air, the reason there is a distance between the Earth and the Moon, is because the quantum fields in those regions are highly entangled with each other. Let's do another thought experiment to test this. What if we take a region of space and we systematically begin to sever the entanglement? We take the quantum states of adjacent regions and we break the correlation. We cut the threads. What happens? The math of the holographic principle tells us exactly what happened. As the entanglement drops to zero, the space between those regions literally shrinks and disappears. The physical distance between them tears apart. Space rips. Without entanglement, space pinches off into separate, isolated islands. Space ceases to exist. So what creates space? Space is not an empty box. It is not a fundamental feature of reality. Space is the shadow cast by quantum entanglement. It is the geometric consequence of quantum information interacting. If you knit enough entangled particles together, they produce the illusion of distance, volume, and geometry. Space is the sweater woven from the yarn of quantum mechanics. But what about time? We've dismantled space. We've turned it into a hologram, a web of spin networks, a tapestry of entanglement. But time feels different. Time is a river. It flows relentlessly forward. It drags us from the cradle to the grave. You can move back and forth in space, but you can only move forward in time. Why? What creates time? To understand time, we have to look closely at a teacup. Imagine a beautiful porcelain teacup sitting on the edge of a table. You accidentally bump it. It falls to the floor and shatters into 100 pieces. The hot tea splashes everywhere, and now sit and wait. Wait for the tea to gather itself back into a puddle, leap up into the air, while the porcelain shards, reassembled perfectly, fuse together and land back on the table exactly as they were. You will wait until the end of the universe, and it will never happen. Why? If you look at the fundamental laws of physics, Newton's laws, Maxwell's equations, even quantum mechanics, they are totally symmetric in time. The equations work equally well forwards as they do backwards. At the microscopic level, if you show me a video of two atoms bouncing off each other, I cannot tell you if the video is playing forward or in reverse. Both are perfectly allowed by physics. So if the microscopic rules of the universe don't care about the direction of time, why does the macroscopic universe care so much? Why does the teacup only break? The answer was discovered in the late 19th century by an Austrian physicist named Ludwig Boltzmann. Boltzmann figured out that the arrow of time is not a fundamental property of time itself. It is a property of statistics. It is about probabilities. It is called entropy. Entropy is a measure of disorder, or more accurately, a measure of how many ways you can rearrange the microscopic parts of a system without changing its macroscopic appearance. Let's look at the shattered teacup. There is only one way to arrange those atoms to make a perfect whole teacup. But there are billions, trillions, quintillions of ways to arrange those same atoms as a pile of broken shards on the floor. So as things interact, they naturally evolve from a state of low probability, a perfectly ordered teacup, to a state of high probability, a disordered mess. The universe moves toward high entropy simply because there are infinitely more ways to be disordered than to be ordered. This statistical march toward disorder is the arrow of time. We feel time passing because we are observing the universe becoming messier. Our memories work the way they do because recording a memory increases the entropy in our brains, and we remember the past and not the future because the past had lower entropy than the future. But what does this mean about the creation of time? It means that the flowing nature of time is an illusion born from our blurry vision. Imagine reading a book. The story flows from page 1 to page 300. You experience it linearly. You feel the tension, the progression of time. But if you look at the physical book, all the pages exist simultaneously. Page 300 exists at the exact same moment as page 1. The flow is just how you interact with it. Einstein's general relativity paints exactly this picture of the universe. It is called the block universe. In the block universe, past, present, and future all exist at once. Space-time is a giant, frozen, four-dimensional block of ice. The Big Bang is at one end. The end of the universe is at the other. My birth, my death, the Roman Empire, the flying cars of the year 3000. They are all just coordinates embedded in this giant block. Einstein himself wrote shortly before his death, "For us believing physicists, the distinction between past, present, and future is an illusion. Present and future is only a stubbornly persistent illusion. Time doesn't flow. Time is. The entire history of the universe is just laid out, and our consciousness is somehow dragging a spotlight along the time axis, illuminating one slice at a time, calling it now. But now has no fundamental meaning in physics. Now on Earth is totally different from now on a planet orbiting a black hole due to time dilation. But let's go deeper. Let's go back to the quantum foam, to the realm of loop quantum gravity and holography. If space is emergent, if it is built out of entanglement, is time emergent too? Is there a state of the universe where the universe is not in a state of the universe? Time does not exist at all. Yes, in the most advanced equations attempting to combine quantum mechanics and gravity, something terrifying happens. The t variable, the variable for time, drops out completely. It disappears. The Wheeler-DeWitt equation, which is essentially the Schrödinger equation for the entire universe, describes a universe that is completely static. Nothing happens. If the fundamental reality of the universe is a timeless, static quantum state, how the hell are we experiencing change? The physicist Carlo Rovelli proposed a beautiful solution called the thermal time hypothesis. Rovelli says, look, time is not a property of the fundamental quantum reality. Time is a macroscopic illusion generated by our ignorance. Imagine you have a balloon filled with air. You measure its temperature, its pressure, its volume. These are macroscopic properties. But you are completely ignorant of the exact positions and speeds of the trillions of individual oxygen and nitrogen molecules bouncing around inside. You don't have enough computing power to track them all. Rovelli argues that time emerges from this very ignorance because we are large, macroscopic beings. We cannot see the fundamental, timeless quantum states of the universe. We only see fuzzy statistical averages. And just like temperature emerges when you average out the motion of molecules, time emerges when you average out the quantum state. Time is a thermodynamic effect. If you were a godlike being capable of tracking the exact quantum state of every particle in the universe, time would vanish. You would see the static, timeless block. But because we are blind to the microscopic detail, our macroscopic perspective forces the universe to appear as if it is changing. Time is the heat of our quantum ignorance. So what creates space and time? If we weave all these staggering discoveries, we can create a tapestry of knowledge that is both beautiful and practical. Together, general relativity, quantum mechanics, loop quantum gravity, the holographic principle, ER equals EPR, and entropy, we arrive at a picture of reality so foreign, so deeply beautiful that it shatters everything our monkey brains evolved to understand. At the absolute basement of reality, there is no space, there is no time, there is no stage, there is no clock. There is only a vast interconnected web of quantum information, mathematical network of probabilities and entanglement, completely devoid of geometry. Through the intense interactions of this quantum information, patterns begin to emerge. The threads of entanglement link up, weaving together like a grand cosmic tapestry. This weaving process projects a hologram. The density of the entanglement creates the illusion of distance. The geometry of the network creates the illusion of volume. The statistical march of its interactions, moving from order to disorder, creates the illusion of a flowing clock. Space and time are not the canvas on which the universe is painted. They are the painting itself. They emerge from the complex dance of quantum bits, just as the wetness of water emerges from the interaction of dry oxygen and hydrogen atoms. But you can't take an oxygen atom and say, here's the wetness. Wetness is a collective behavior. Space and time are the collective behavior of quantum entanglement. Now, pause for a moment. I asked you at the very beginning to hold your hands out and look at the gap between them. Do it again. Look at that empty space. Knowing what you know now, what do you see? You are not looking at emptiness. You are looking at a boiling ocean of quantum foam, fluctuating billions of times faster than a blink. You are looking at microscopic wormholes, invisible threads of quantum entanglement, desperately holding the fabric of reality together, preventing the space between your hands from pinching off into nothingness. You are looking at a three-dimensional projection from a two-dimensional boundary located at the edge of the cosmos, and the time it took you to raise your hands, it was just a statistical illusion, a byproduct of your own biological ignorance dragging you through a frozen block of eternity. We have peeled back the layers of the universe. We have looked behind the curtain of the great cosmic magic trick, but physics is a relentless master. Every answer breeds a deeper question. We know that entanglement weaves space. We know that entropy weaves time. But what weaves the entanglement? Why are there quantum bits at all? Where do the rules of the hologram come from? The universe is a book written in a language we are only just beginning to decipher. We have read the first chapter, the chapter on atoms and light. We are now reading the chapter on space and time. But the rest of the book, the pages are still blank. The great mystery remains. And that, my friends, is why we keep looking. That is why we would keep calculating, keep arguing, and keep wondering, because nature is hiding its greatest secrets just out of reach, waiting for the next curious mind to ask, but what's underneath that? The fabric of reality is right there between your hands. The ultimate cliffhanger is, what are you going to do with it? Thank you.